So welcome everyone. In this session I'd like to talk about creating large-scale complex React applications. And in fact, most of the stuff I'm going to talk about is not even specific to React. Some of it is, but most of it is more broadly applicable to any front-end browser-based application. So just to give it a bit of context, the experience we gained was building an application to prevent this from happening. This is what was the Deepwater Horizon in the Gulf of Mexico burning down. This was not using our software, so I can't take any blame for this happening. But basically the software we developed was used on drilling rigs like this and production platforms and some onshore sites where they were producing oil and gas. Well, it's kind of heavy industrial equipment, requires lots of maintenance. And maintenance, well, it's kind of dangerous in those places. Like if you've got a gas line and there is a valve in there which needs to be replaced, you kind of have to open up that gas line, which means that even if you close up everything, still some gas will escape and potential for danger is there. Now, by itself, that isn't too bad, but if someone else decides, well, I need to do some welding, I'll go start welding just next to it, then you've got sparks with free gas, and these kinds of things can happen. Not good. So who am I? My name is Maurice de Beijer. I'm an independent software consultant, also a trainer. Most important thing here is my Twitter handle, Maurice de Beijer. I'm going to tweet these, or I'm going to upload my slides to SlideShare and the demos to GitHub, and I'll tweet that. I'll probably do that tomorrow morning. But if you just check my Twitter handle tomorrow morning, you'll be able to find those. So what are we going to talk about? Well, first I'm going to talk about stuff you run into with HTTP, because it turns out that HTTP, yes? Closer? Oh yeah. I can hear the difference. So the first thing I'm going to talk about is HTTP and doing AJAX requests. Because it turns out that if you do HTTP requests on your desktop or your laptop while developing, it usually just works. It's all local machine and really fast. But if you go out on the internet, start using 3G connections or satellite collections like we had to, then it isn't quite as easy. I'll talk a bit briefly about scaling, because scaling takes some requirements, and turns out it's a lot easier if you think about that up front from the start. Then I'm going to talk a bit about different programming language stuff we did, TypeScript, ESLint, and that kind of stuff. A bit about Webpack as well. And finally, I'll talk about error handling inside of the browser and some of the stuff that can happen there. But first, like I said, HTTP. So the first thing is not actually about HTTP itself, it's about how you set up things. If you've got a real small application, it's fine to just create a simple endpoint on the server, but not the same. You can't remember all those details. It's kind of too hard to remember. So what we resorted to was generating a lot of our code. We basically use Swagger, which is a service you can use on the internet, or you can download it, install it on your own machine. And you describe what your endpoints should look like and what the data is you're going to use. And based on that, you can start generating client-side and server-side contracts. Now, as an example, I've got the Swagger editor open here. And on the left-hand side, you can see the data contracts. We're actually more than a data contract. Over here, let me zoom in a bit more. So that should be readable, I hope. If I zoom in any further, we just won't see anything anymore. But basically, there is a list of paths here. So the path movies. And we can do a get there. And there is some description stuff here. And there is something about responses. So we can get a 200 response, so the basic OK. And it returns something. So over here you can see it returns an array of movies with a reference to how that movie looks. Or it can do an error in case something went wrong. So if I scroll down to the bottom, let me quickly scroll down. Over here, I've got my data contracts. So the movie contracts right here. And it's basically an object. It has a couple of required property. So there is an ID here, which is in type integer. There is a title, which is a string. There are some scores there, which are integers between 0 and 100. There is a, where is it there? There is a cast, which is again an array of cast members, which is down here. This is the cast. So again, an object which has a required ID and a name and how they look. So with this, creating a fixed description of what everything looks like is a lot easier. Next, we need to get our code, and the online version has a generate client option here, where there is a bunch of options, the same for server. With client, I didn't see all of them, it kind of scrolled out of the screen. But you can see here, you can generate it basically as Node.js or as an ASP.NET 5. We were actually using ASP.NET on our server, so we used that side. And we used, well, TypeScript on the client, which is in here. It's just scrolled out, but it's one of the options. So that generates a bunch of code, which I've already downloaded. And here we can see the server. All the stuff for the server is in there, a simple node server, a client. And I've got a little demo script with basically just exercises that service. So let's run my server, do all the one-handed stuff. So node demo. And you can kind of, well, there isn't a whole lot to see, but you can see that a request was made to the server. At least you can't see that the request was made, but trust me, this actually made a request to the server. And there was no error at the bottom here. It says errors null. But suppose I change something in here. Let's say that name property here was required. And I remove that. And tab back. Now I do the same again. Now you see an actual error. The server validated my objects against the Swagger definition. It was no longer valid, so it was immediately rejected. No code required at all. It automatically does all those kind of checks. So it's the kind of thing you don't want to start with if you've just got a small project. Then it's just overhead. But if you've got hundreds of endpoints, lots of data contracts which you have to maintain, which migrate over time, properties get added, dropped, renamed. You have to make sure that the client and the server-side code stays in sync. Then using something like Swagger helps a lot. So the next thing about HTTP is doing actual HTTP requests. And like I said in the intro, if I do this on my development laptop, it typically just works fine. It's localhost. Localhost is always available. Even if there is no network, localhost is still available. It's fast. It's the local loopback adapter. That takes just milliseconds. So everything runs really fast, and I don't really get strange things. But when you start working with offshore production platforms or stuff located somewhere in Siberia or something, then your internet connectivity is not going to be quite as good. If you run over a satellite connection, anyone know roughly what your average latency is going to be for over a satellite connection? 100 milliseconds. I wish. No, count on a second. It's going to take a second latency for every request. So even if you've got 0 time on the server, a request is still going to take around a second. Anyone know for a 3G network, just a regular 3G network outside of the big cities where you've got really good coverage? Yeah, think about 500 to 600 milliseconds. Just latency. So things are going to be a lot slower. But it's not just slower. You're going to see things fail, just things time out. One request might go through, the next request might not. Now, if you never experience that on your local machine, it's kind of like, well, shit happens. It goes into the field, and there it fails occasionally, but you can't reproduce it. Works on my machine. So we actually made sure that it started failing on our machine, and we had all the requirements in place to handle that. So we had some middleware called the Chaos Monkey, inspired by the Netflix Chaos Monkey. Now, we didn't use their code, we just wrote some code ourselves. It's nowhere nearly as sophisticated as what they've got, but it did a couple of things. One, it would randomly drop some messages. So it would take, say, 5% of the messages and just drop them all together. And it would take another 5% of the messages and would return a server not available kind of error, just maybe a 500 or a 503 kind of status, something where the server can't respond. So we're kind of simulating those errors which will happen in production. And we had code to make sure it worked. So to give you an example of how that works, let's stop this server. And let's start another one. npm start with a T and a single M. It will work better. So this is going to start up a simple server listening on port 400 and a simple React application just done with create React app, which will proxy some requests to that server. Now that server is set up using that Chaos Monkey, so it will occasionally fail, at least a simple clone of the Chaos Monkey. And assuming my page actually loads, which would be nice if it did today, there it is. You can see there are two buttons here. The first two requests does exactly what it says. It does two requests to the endpoint. The first will respond with one, the word one. The second will respond with the word two. So if I click it, you'll see 1, 2. Well, the one was very hard to see, but it was there very briefly. And it basically does that. So usually, if I click this, it does 1, 2. But you'll see occasionally we end up with 1. Because we randomly introduce latency here. It's going to take somewhat longer for some request. So occasionally the request will resolve out of order. The second request will resolve first, and the first request will resolve last, which kind of gives errors. So we actually saw this in production. We had a list of work permits, and the user could click on the work permit to see the details. But they might click on the first one, then click on the second one, but because of requests resolving out of order, while they clicked on the second one, the second request would complete first, and they would actually get the first request or the first work order last and see the wrong details with the wrong selected item in the list. So there is no simple way to fix this. Let's go to the code. Demo poly, in source, in app.js. I've got do two requests here. And if you want to fix this, and you really want to make sure you receive only the last request, you really should cancel the first request. Turns out that depending on how you do your HTTP requests, you may be able to or may not be able to do so. In this case, I'm using the HTTP fetch API, so the new standard API to do AJAX request. Well, fetch is kind of nice, kind of low level, but kind of nice, but it also does not have a way of canceling requests. So I can't basically say, well, go and cancel the first request because we're starting the second, and forget about it. Instead, all I can do is say, well, if the first request or the second request is started and finished, let's just ignore any results from the first request. So by enabling a little check from, okay, is the request state already set, then that request should work. So now, no matter what I do, we should always end up with request 2 as last. And maybe request 1 was displayed, maybe we just completely ignored the result, but at least it's predictable. But like I said, canceling would be better. Another problem is failing request. That's what the second button does. It does another request and it basically gets the current time. So if I press that, it retrieves the current time from the server, displays it, and it does so again. But once in a while, in fact in this case once every 3 requests, because I've kind of made this fail a lot, it is just going to get a 500 error status back and it says fetching, but it's basically just failed. So after that it works just fine again. It's just once in a while it breaks. So fixing this is a lot easier. There is an open source library called Poly, which I wrote a few years back. And this basically does transient error handling. It will detect error situations. Failing HTTP requests is one of those, but it could be anything. It could be any kind of action you're doing which could fail but is retryable. And this will basically detect that HTTP 500's return status, and if it sees one of those or maybe a timeout, it will just retry the same action. So let me enable that one. And this one. So now I've basically just wrapped the fetch code with a call to Poly. My app is retried, and now once in a while it will say fetching, but I've actually told it to delay slightly longer than I normally would. Normally I've got delays of 100 milliseconds and 200 milliseconds, and just stagger it like that. I've kind of made them a bit larger so we can actually see the retry here. And now it's waiting for 1 second before it retries, but it automatically retries and we still get the response. So that takes care of a lot of those HTTP errors. In case of a complete timeout, it's still going to retry, it's just going to take a bit longer, but if there's no response at all, it will detect that and retry just as well. So another issue with HTTP, or issue, it's not an issue per se, but the issue is HTTP caching. So in general, if you're going to do a lot of requests, you want to start using caching for static data. Suppose you've got an endpoint returning you a list of countries. Well, the list of countries in the world doesn't change very often. Occasionally we'll get a new country, or maybe one will disappear because of some political action, but for the most part that is relatively static. So that's the kind of data we want to cache. There's also data you typically don't want to cache, or maybe have some kind of version check, like in our case permits. They would be changed relatively often. Now we would still want to do some checks to not download the same permit every time. So we use something called e-tags, which is basically a version of the document you retrieve. And the next time you request that, the browser will send that along and basically say, well, can you give me this if it has changed, and if not, just let me know, well, and I'll use the one I've got in my cache. But there is a problem with caching. If you're doing RESTful services, you might use an accept header to do content negotiation. And by default, the browser and other middleware or devices out there will use just the URL to decide if something needs to be cached. So just because you asked for something in a JSON format, now someone else asked for that same cached resource in an XML format, he's going to get JSON instead of XML. He's probably not going to be too happy about that. The same with authentication. You might request something, you might be authorized for it. You'll get that response back and it might be perfectly static, so cached. Someone else is going to ask for it. He might not be authorized to see it, but it's still going to be read from the cache. So there is an HTTP vary header, which you can basically specify in a request, and that contains all the headers that the caching infrastructure should use when deciding whether a cache entry is valid. So always make sure to include at least the accept and the authorization headers in there, but any other headers you find useful. One we added, which we found very useful, is the application version. Different versions of the application might add or delete data. They might change the data structure somewhere. Well, guess what? If you just happen to retrieve a cached version of the previous structure of the application, you're going to run into issues again. So that's another thing you want to add to the vary header. Another thing which is not exactly obvious if you start looking at caching is what happens if you don't specify cache headers in your responses. The HTTP caching spec is kind of very detailed, and there is a lot of stuff there. If you add these kind of headers, this will happen. If you add these, that will happen, etc. Except for one case. They kind of left out one case. The case where you don't specify any caching headers in your response. Chrome and Firefox used to say, well, if you don't specify that something should be cached, we're not going to specify it. We're not going to cache it. Older versions of Internet Explorer said, well, if you don't say we can't cache it, we will cache it. So you'll get different default behavior. That IE problem is mostly gone because IE is slowly dying away and Edge does things correctly. But it's not just browsers that do caching. There is all sorts of infrastructure. Again, if you're working on your local machine, it's just the browser and the server. But if you're going through satellite connections, there will be caching middleware machines, all sorts of caching to optimize requests. They might not do the right thing. So always make sure to include those caching headers. So scaling is also an interesting thing. Scaling out in this case. Because basically there are two options when it comes to scaling. You can scale out, say, get more machines, or you can scale up, get a bigger machine. Scaling up is typically quite easy to do from a technical standpoint because you've still got one machine and you're adding a stronger, bigger machine, but your whole architecture doesn't change. Scaling out is a little harder. Now you're working with multiple machines. You're going to distribute traffic over different machines, and you can get very different responses for different machines. So the first thing you want to make sure is that you always start with 2 machines, even when developing. Scaling out is hard, going from 1 machine to 2. And with machines here, I'm talking about web servers or database servers, machines of the same category. I'm not talking about saying, well, I've got one machine which has my website or web application, the web server, and my database, and now I'm scaling out to move my database to another server. That's easy. It's going to increase the latency a bit between the two, but other than that, it's no biggie. I'm talking about scaling out in, I'm going from 1 web server to 2 web server, or 3 or 4. If you maintain any form of state, you're probably going to run into issues. You can configure sticky sessions, where one client will always connect to the same server, but sooner or later you'll run into that server not being available and the request actually going somewhere else. In general, always use round robin and always make sure there is no state. So we use this. We basically had Chaos Monkey again. So anytime in development we would run 2 copies of our server software with the Chaos Monkey in front, and besides dropping some of the messages, it would also round robin to the different servers. So any potential accidental state we kept on the server would be detected and would show up during development and testing and not in production. So writing code is actually a lot harder than you think. We were on this team with a dozen engineers, at least engineers and testers. They were quite experienced, like there were no junior developers. There was someone who had a bit less experience than the others, but for the most part, these were all very, very experienced people. So we knew we had to get help from all the systems we got. So we started using TypeScript. Now, whether you use TypeScript or another type checker like Flow doesn't really matter. The fact is you want a type language if your system becomes bigger. If you've got a small system, just a few people working on it for maybe a few weeks, then you can remember stuff and everything is fine. But if you've got hundreds of types and services and lots of stuff working together, making changes is going to become harder and harder, especially with a dozen people working on a system. What's the impact of my change? Not quite sure. I change something on the server, something on the client might fall over. Like I said, we were going to generate client and server side interfaces and types anyway, so they would be consistent. But with TypeScript, or at least with type checking, we would know that if we accessed a property or were calling a method, at least it existed. It doesn't mean you won't have bugs. It's just a specific type of bug, which will mostly go away. If you do that with pure JavaScript, you'll run into lots of undefined is not a function kind of things, or you're concatenating a few strings, but one of them has a typo, so again you get undefined there instead of what you want. So just use one of these things. We also used ESLint, and because we're using TypeScript, we also use TSLint. We use both of them. Basically do lots of static analysis on our source code. TypeScript prevented the undefined is not a function kind of error. ESLint and TSLint prevented lots of other errors. Missing semicolons, which can do all sorts of weird stuff. Just being consistent with code, with spacing, not forgetting prop type definitions in React. All those kind of things are done with ESLint. Now, one advice, we kind of, yes?
If you use the TSLint, is that still helpful to use ESLint as well?
If you're only writing TypeScript, no it isn't. But we had a combination of TypeScript and JavaScript. Because when we started, TypeScript did not support JSX syntax yet. That's why we had both. But when we started, we kind of figured, well, we're all very experienced. We don't need too many rules. And we kind of created a small rule set and worked with that. We kind of regretted that afterwards, because even though we thought we were all very experienced and wouldn't make some basic mistakes, it turned out we did. And I was as guilty of it as some of the others were. So after a while, we decided we had to increase the number of rules in our lint configurations, which means that lots of lint rules were all of a sudden broken, and you kind of had to go in and fix them. Now, ESLint has this wonderful option --fix. So you can run ESLint with the fix option, and most rules it's able to fix. Not all of them, but rules like indentation, which is wrong, or missing semicolons, it will inject them. And usually it will inject them in the right place, so it will actually fix the problem. Not all rules are automatically fixable though. And for TSLint, the TypeScript linting, the --fix option doesn't exist yet. That's something which they're working on, so that will be there in the future. My recommendation is to start with the Airbnb rules. Airbnb has a very good set of rules. It doesn't cover TypeScript. As far as I know, they don't use TypeScript, but it does cover ECMAScript 2015, it covers React and lots of other cases, so it's very good. Now, some of the stuff in there is kind of like, well, your program is not going to break. Like, should you use 2 spaces or 4 spaces indentation? Your program is not going to break if you change that. But there is other stuff like whether you want to validate prop types or not, which could potentially affect your programming or the result of your program. So I would highly advise you to use that. So another thing we used was Webpack. We actually started off with Browserify, but we quickly run into performance issues with Browserify. So quite early in the project, we switched to Webpack. A Webpack is that bundler which will basically load up all your source code and even images and CSS, etc. It can do quite a lot. Bundle that together, call Babel and the TypeScript compiler to transform stuff and produce a couple of bundles to download into the browser. And that worked fine. But we started running into some performance issues. Like at first, it ran in a few seconds, no problem. But then we kept on adding code and adding code and adding more code. And it started gradually getting slower. And it's one of those things where if you put a frog in boiling water, it will jump out. But if you put a frog in cold water and you turn up the heat, apparently it just stays in there until it's boiled. Well, we didn't stay until it was boiled, or we were boiled, but it took a while before we actually started fixing this. And the first thing was the Common Chunks plugin. That's a plugin you'll read all about, and it's quite common. Like if you've got a lot of common code between parts of your application, use the Common Chunks plugin to remove that common code into a separate bundle, which you can separately download, which is a very good principle. But the problem with the Common Chunks plugin is that common code, like your React, Lodash, and all of that stuff, which is completely static, is evaluated every time, which, because it's completely static, is a waste. Like once in a while you'll upgrade React, but restarting your Webpack is not an issue then. So there's actually a better way of creating a static library like that, and that's using the DLL plugin and the DLL reference plugin. It basically means you've got two Webpack configurations, one for your static DLL, that will use the DLL plugin. It will create a JavaScript bundle and a JSON file, which is basically a manifest of what's in there. Then inside your application bundle, when you run Webpack, you use the DLL reference plugin. You basically tell it, well, there's a manifest file which contains all the stuff which is already available, just use it from there. Because all of that's already been done once, it doesn't need to rerun all the time, it doesn't need to be really evaluated, and that saves a lot of code. Because even though we were writing quite a lot of code, it's still like React, Lodash, and those standard libraries were quite a large part of our code. So just removing all of that from our Webpack bundle saved a lot. But it saved a lot, but not enough. It still turned out that all the code we were writing, every time you made a change and you saved, a lot of evaluation was going on. And a lot of code which wasn't actually changed still got evaluated. So it turns out there is this loader for Webpack which is brilliant. It's called HappyPack. And it addresses the issue in a few different ways. First thing it does, it says, well, all of this is JavaScript running in Node. Node is single threaded, so that's one core doing something. And my laptop has 4 cores, so that means 3 cores are not doing anything at all. How about we start using them? So they actually use web workers and start parallelizing compilation tasks, so it runs faster. It starts using the whole machine instead of just a tiny part. But it actually does one better, because that's just the first time you start it, it's already faster, and it's maybe a third faster or something. But then you can specify this cache option. And with the cache option, it starts writing out metadata about everything it's transformed. And then if you restart it, or it has to reevaluate something, it's going to look at that cache and see whether it's actually changed from previous time. And if it hasn't, then it basically will conclude, okay, I don't need to transform this, I don't need to run Babel, I don't need to run the TypeScript compiler and all the other loaders, etc. I can just take the previous result and return that. That sped things up a lot. Now, HappyPack is compatible with most TypeScript loaders. Unfortunately, it was not compatible with TS loader, which is the TypeScript loader which we were using at the time. Turns out there is another. That's the awesome TypeScript loader, which is still not compatible with Happy Pack. That's actually an issue in the TypeScript compiler itself, but it implements a lot of the Happy Pack details on its own. So even though it does it differently, it kind of has the same effect. And between using the DLL reference plugin and these two loaders, our build times from initial startup would go down from around a minute to around 10 seconds. And incremental builds would be like, well, 0.2 to 0.5 seconds, which was a lot better. That's kind of where you'd like to be. So another issue is errors. Everyone hates errors and wants to pretend they don't exist, but they do. And you can ask your end users have you had any errors? And they will probably say no. And you can leave it at that. You can trust them. But the reality is that usually users will think that they did something wrong, and whenever an error occurs and it wasn't actually a program problem. So if you want to know about errors, you really have to start tracking them. So that's another piece we built. Basically start logging all the errors that occur in the browser. So hooking up the window on error event, tracking all AJAX requests, seeing if errors went, doing anything which was basically asynchronous, adding a catch handler to that, logging all of those, and sending those to the server. Now, one thing you might run into if you start sending those to the server is that the error might be a result of you being offline in the first place. You're expecting to get something back to the server, but the server is unreachable, and that causes a number of other errors. So, as a result, we actually started storing all the errors in local storage. Could use IndexedDB, but we decided to use local storage. And only sending them to the server sometime later. There was actually a second reason we did that. One, so they stayed around if the server was not reachable and we could send them later. But the other issue is, well, you might have an error somewhere in the loop. So you might have some AJAX request return maybe, and you try to reach a property from it which doesn't exist, call a function on it, maybe to string something, and you'll get an AJAX request and 1,000 errors in rapid succession. Do you want to send 1,000 AJAX notifications to the server from each specific error? No. You're just going to eat up more bandwidth, and they're all going to be the same anyway, so you don't need all of them. So what we basically did is said, well, we've got an error window of 1 minute. If we detect the same error with the same message and the same call stack within the same minute, we would just increment a little counter so we would know how often it happened, but not send them individually. So we would basically say, well, this undefined is not a function, error occurred 100 times inside of this minute. And at the end of the minute, we tried to send it to the server. If it was available, we would just remove it from the client. If the server wasn't available, we would just keep on trying, maybe days later, until the client was available. So even if someone took his laptop off the network, put it in a plane, started working in a plane where he was getting errors all the time, well, eventually he would get back into Wi-Fi or 3G connection again. So eventually we would get those errors. But don't forget to do that, otherwise you won't see any errors inside the client. Now let me actually start another server. Stop this one. And show what happens. Ooh, that's not what I wanted to do. I wanted to go here. npm start this project. So that's another simple React application, another one done with Create React app. But in this case, I want to show what happens when you have an error when rendering. So this application should load, and there should be a single button, and every time I press that, we should see the current time on the screen update. And it would be nice if it actually rendered. There it is. So you can see 2 times here, the render time and the set state time. Basically, every time I hit this update button, the handler behind that, the click handler, will set the current date or the current time in the state, which will cause it to re-render. The first method, the render time, is actually just a new date inside of the render and displaying it. But right now, they're basically updating together nicely. So let's break this and see what happens. Demo error, source, app. Let's assume I said, well, because we really are only interested in the time part, I'm just going to store the time in the state. But in my render function, I'm still using toLocalTime string on the object in the state. Now, of course, that's perfectly valid on a date object, but not on a string. Then that will cause an error. So switch back, and now if I click update, nothing happens. But notice that neither of these times are updated. The render time, which was just calculated on the fly, doesn't update either, even though it's above the one causing an error. So this is kind of the typical behavior in a React application if there is an error in a lifecycle function. Nothing happens. In some cases, you'll actually completely crash React. But in most cases, you'll get something like this. Well, an error happened. And what actually happened? Well, if I open up my developer tools at the bottom, here you can see that errors actually occurred. But other than that, you won't be able to see much. And end users don't run with the developer tools open, and developers quite often don't either. So we're using this React Safe renderer. And if I enable this piece of code and go back, we can do the same. Now if I click update, I get a very clear error. In this case, it's just an alert box, but you can use whatever UI we want. We didn't actually use an alert box, we used a component. But it will tell me exactly about what went wrong, and now I can make it much more clear for the developer and the end user as well that something was wrong. Basically, inside of React, all the lifecycle functions, so not just the render, also the component will mount, component did mount, component will receive props, etc. All of those suffer from this problem that if some unhandled exception is thrown there, then it just plays havoc with the React lifecycle model. So use something like this. So the React Safe renderer. Dan Abramov has an alternative to this, which is also quite nice, except that only covers problems in the render function. This one actually uses all the lifecycle functions, which is why we used this one. React Redbox is a nice component if you actually want to display this to an end user. So show this on the screen. We did use this during development for a while, not for end users. It's a little too intrusive for end users, but we would make something on the screen available for end users to know, to see that something went wrong, except it was just a little icon at the top. They would click on it and they would get a little display about what kind of errors occurred. But during the development, this is the kind of thing you want clearly from this .props is not a function with the stack trace and all the stuff around it. Very useful. So with that, I'm at the end. So just a short recap. Remember, HTTP on your local dev machine is perfectly reliable, perfectly fast, but in the real world, it's not, especially if you go mobile or satellite. Scaling out from 1 to 2 servers is hard, so make sure you do that right from day one. Don't start doing that for the first time when you run into load problems, because you'll scale to the second machine and you'll have more than just load problems. Use programming languages and linters and those kind of things to help you produce good code. It's not going to make your code perfect, but it's going to eliminate certain categories of errors. Webpack is great, but for large projects it does get slow, so use HappyPack or something similar. And make sure to log all your errors and actually check your React lifecycle function for errors, because they get eaten up by default and you'll miss some important clues about how to make your application better. So with that, I'm at the end. Remember my Twitter handle. Tomorrow morning I'll post these slides online, same with all the demo code. I'll push that online so you can download